Hello, this is Captain Chaudhari. Today I am going to talk about the SFBM of these single hold barges. You know, they might be loading ore, and the loading that might end up without trimming may be called a prism loading. So you might load them in such a way mechanically that it forms a kind of prism, right? Or it might be that these barges are, loaded with the manpower on either side or whatever on either side, and it forms a shape like this. We can call it reverse prism. We're going to talk about the SFBM of the barges. So I picked up a numerical from my book. There is a barge which is 80 meters in length, and it weighs 280 tons as light, and it is loaded with 640 tons of ore in such a way that there is maximum height at the ends of the barge and zero height at the middle. So it can be seen this way, that the barge is loaded like this. Okay, so I call it a reverse prism loading. Now the thing is, how to find out what is the load that is acting at different points, right? Because this cargo is not evenly loaded. This cargo is having different height at different points. We can call this point as midships. This is quarter length and this is quarter length point. And just by looking at the diagram, or even by the principle of similar triangle, the height over here is half of the height over here. Similarly, height over here is half of the height over here. Now, if the cargo was not loaded like this, if the cargo was evenly trimmed, probably what would have happened is this triangle would have come here and this triangle would have come here. So the initial statement which can be written about these questions is, while the cargo is loaded in this fashion, if the cargo was level trimmed, then the mean height would have been the height presently at the quarter length point is equal to height at quarter length points, which means that the total cargo, that is 640 tons, if I divide it by the length of the barge, that is 880, will give me 8 tons per meter. This means that the weight that is caused here per meter at this point is 8 tons per meter. Now you can see we can use the principle of similar triangle. If it is 8 tons here, it is 0 over here. In between the two, the weight of the cargo will be 4 tons per meter. And similarly, if this is 8, this would be 16. This would be 16 tons per meter, and this would be 12 tons per meter. So this way we can divide the bars into 8 segments. We'll call it A, B, C, D, E, F, G, H, and I. Now we're going to draw the graph, and before that we're going to find out what is the load at these points. Now load, as I told you, is the buoyancy minus the weight at any given point. Now it is like I tell the boys, like, whatever is your salary, suppose your salary is 10,000 rupees and you are spending 12,000 rupees, 2,000 rupees is the load per month at your family. So load is the difference between the weight and buoyancy, right? So if we consider these points, and we say that the load per unit length is equal to buoyancy per unit length minus weight per unit length. The total buoyancy would be total weight 280 plus 640, 920. 920 tons spread over a distance of 80 meters. 11.5 I get, 11.5 tons per meter is the buoyancy. Now this is the mean buoyancy of the barge. Now looking at the distribution of the cargo and looking at the description of the barge, can I say that the barge will float on even keel? Now barge floats on even keel means the draft is same all over the barge, and if the mean buoyancy per unit length is 11.5 tons, it can be said that at every point along the barge length the buoyancy is 11.5 tons per meter. Let's write down the loads at different points. The stations are A, B, C, D, E, F, G, H and I. We know that load per unit length is equal to buoyancy per unit length minus weight per unit length. Now buoyancy per unit length is 11.5 and that is uniform all over the length, minus the weight of the barge is 3.5 per ton, and you have the cargo per unit length as 16. So this will give me minus 8. Then at B I have 11.5 minus 3.5 plus 12, that is equal to minus 4. At C it is 11.5 minus 3.5 plus 8 giving me 0. At D it is 11.5 minus 3.5 plus 4, that is plus 4. At E it is 11.5 minus 3.5 plus 0, so that makes it 8. At F it is 11.5 minus 3.5 plus 4, so that gives me 4. At G it is 11.5 minus 3.5 plus 8 giving me 0. At H it is 11.5 minus 3.5 plus 12 giving me minus 4. And at I it is 11.5 minus 3.5 plus 16 giving me minus 8. So this is the kind of load curve I get, right? Now to draw the load curve, first of all let us decide what should be the scale of the barge. Now barge is 80 meters long, and now I want to fit this barge of 80 meters into say 16 centimeters. So the scale which I can take is 5 meters is equal to, length scale is 5 meters is equal to 1 centimeter. Now I can call these points as A, B, C, D, E, F, G, H and I. Let me select the scale. Say I want to fit the load curve into 8 centimeters, so I can take the scale as, for the load I can take tons per meter is equal to 1 centimeter. So I will draw it a little closer to fit the graph. So 1, 2, 3, 4, 5, 6, 7, 8, and same thing here, 1, 2, 3, 4, 5, 6, 7, 8. Now let's plot the load curve. 1, 2, 3, 4, 5, 6, 7, 8. I start from here and you can see that at C it is 0 and it is becoming maximum at E. So it would continue traveling like this, and on this side also a straight line, and it is going to reach this point. So you can see the load curve. It is in our convention, in our sign convention, it is coming opposite to the loading. Loading has got cone this way and the load curve has got cone this way. So this is the situation of load curve, and we'll try to build up the SF curve as well as BM curve on this graph only. Let us do the calculation for SF and BM. Now let us find out the SF ordinates, and as I told you, area under the load curve to the left of point under consideration will give me SF ordinates. So SF at A should be 0, SF at B should be area of this trapezium. This side is 4, this side is 8. The mean is 6 multiplied by the distance between A and B, that is 10 meters. So 6 into 10, that gives me minus 60. Minus 6 into 10, that is minus 60. Now this is 4 and this is 10. 4 into 10 divided by 2, that is the area of the triangle. So that means 20 minus 20. So at C it will be minus 60, total area minus 20. Total becomes minus 80. Now if this is 20, this also will be 20, this will be 60, and we keep adding the area as we go from left to right. So it will be minus 80 plus 20, that is minus 60, and then minus 60 plus 60 equal to 0. So at E we are getting the value of SF to be 0. At F it will be 0 plus 60, that is 60. At G it will be 60 plus 20, that is 80. Then I have 80 minus 20 over here. 80, this is minus area. 80 minus 20 is 60, and then I have 60 minus 60 equal to 0. So the shear force value starts from 0, ends at 0, and I'm expecting that the shear force value is maximum at the point where the load curve intersects the x-axis. Let us decide the scale. Now this extent is 8 meters. This extent is 8 centimeters over here, 8 centimeters over here. Now if I look at the maximum value of the shear force, that is 80 tons, I might take a scale that 10 tons equal to 1 centimeter, that is the scale for SF, right? So if I write down the SF values 10, 20, 30, 40, etc., and minus 10, minus 20, minus 30, minus 40, etc., and try to make the curve, it is minus 60 for B, and for C it is minus 80, and at D it is once again minus 60, and at E it is 0. So the SF curve goes this way, and similarly on the other side the maximum value of SF is going to be 80, 10, 20, 30, 40, 50, 60, 70, 80 over here, and it is going to be at this point, and we are going to have similar curve on this side also. So as I had said before, if the previous curve is a slant straight line, the next curve will be curvilinear. So we have curvilinear shape of the shear force curve. Now area under the SF curve is going to give me BM. If we divide the SF curve in these kind of segments, the area under this part of the SF curve can be found out by Simpson's third law, where ordinate at A is 0. At A the ordinate is 0. At B the ordinate is 60. And at C the ordinate is 80. Right? We have the multiplier as 5, 8 minus 1, and the uniform distance between the ordinates is 10 meters. So H is equal to 10 meters. 0, 480 minus 80. So that is 400. So H upon 12 into 400. That is the area under the SF curve up to B. So let us see, it is 4,000 divided by 12, giving me 333.3. So this area is 333.3. Now if I have to find out what is the area in this part of the curve, then instead of doing 5, 8, minus 1, I should write 5, 8, minus 1. So this is once again 480, but this is 400. So the total becomes 880, and the area will be 8800 divided by 12. That gives me 733.33. So this part is 733.3. Let us tabulate the bending moment, that is tons meter curve. Right? At A the bending moment is 0 as usual. At B it is minus 333.3, and at C it will be minus 333.33 plus 733.33, that is 1066.66. And now 1066, I have to add 733.33. That gives me 1799, 1799, 1800, minus 1800. And then you have 333 plus 333.33 gives me 2133. 2133.33. Now, because the barge is loaded symmetrically about the midship, we can say that the bending moment curve will be mirror image about the midships. So we can actually calculate the area under the SF curve in the similar manner. Otherwise, we may simply write down it will be minus 1800 here, and then minus 1066.66 here, minus 333.33 over here, and 0 over here. Now, what kind of scale we should select? The maximum value is at E 2133.33. Now 2133 divided by 8, because we want to extend it to 8 centimeters. So we can probably take a scale of 300 tons meter is equal to 1 centimeter. That is a bending moment scale. So it is 0 over here. This is minus 300, minus 600, minus 900, minus 1200, minus 1500, minus 1800, minus 2100. Okay, so we start with B minus 333, so it would be somewhere over here. At C it is 1066. 1066 would be something like this. D it is minus 1800, so over here. E it is 2133. So if you see the BM curve, it goes this way, concave in this region and tending to become convex in this region. This is because the SF curve is going downwards in this region and goes upwards in this region. So this is going to be the shape of the bending moment curve. Similarly, we can say that it is mirror image on the other side. The entire bending moment curve appears to be hogging. The ship is hogging. Entire BM curve is on the negative side, and as per our convention, the negative bending moment is hogging. So maximum bending moment that is experienced by the barge is 2133.33 tons meter, right? And if we want in kilonewton, then 2133.33 into 9.81, that gives me 20927.96. So 20928 kilo Newton meter is the maximum bending moment that will be experienced by the bars and hogging.